Okay, sample problem 7.5. So I'm assuming you've watched the, how many videos? I put on the two videos. Yeah, stress transformation and, wait a minute, Moore's circle in 3D and then stresses in thin-walled pressure vessels. So we're going to jump right to stresses in thin-walled pressure vessels. And this is the example we're looking at. It's, why is this other window showing up here? This is sample problem 7.5 from your book. Here's this. Okay, I don't know what that screen is doing there. Huh. Let me turn. Oh, I think I know what's happening. Okay. Oh, geez. All right, so we have a pressure vessel here, and this is interesting because this is something that's very common in industry, a pressure vessel. This is a compressed air tank, and it's supported by two cradles here. This is only 8 feet long, so it's not a huge pressure vessel, 30 inches in diameter. But you'll see these, in fact, Praxair uses horizontal pressure vessels a lot. We used to have these thermal swing adsorption vessels that would go up to, well, they could alternate in pressure between sort of ambient pressure and, maybe 200 to 300 psig at most. But there are also, the horizontal ones are supported by a cradle system similar, where it does not exert longitudinal force on the tank. So one of the cradles is basically just there for support, vertical support. So you'd have a cradle where it's maybe the tank is fixed at one end, and then the tank is allowed to expand or contract depending on swings in temperature, ambient swings in temperature, or just process temperature swings. So this is not uncommon to have something like this. I've not seen cylinders welded this way, spiral like that, in the large scale, but I have seen them with plate welding. So it's typically straight lines and stuff, but you do get spiral welding on, I guess, with smaller specialty tanks. It's possible. Anyway, this is a tank with 30-inch OD and 3/8-inch steel plate. And it's butt welded along a helix that forms a 25-degree angle with a transverse plane. So here's your angle here, 25 degrees. Let's see. Oh, spherical end caps. I don't have a lot of experience with spherical end caps. A lot of the ones we used were 2-to-1 elliptical, semi-elliptical heads, which is another common industry practice. But you will see spherical heads out there. Spherical heads are fairly easy to analyze relative to other ones, so this is also good introductory material. But notice the heads have a thickness of 5/16 inch, and that's also not uncommon, is to find different thicknesses between the cylindrical body and the heads. And so you'll have you have an internal gauge pressure of 180 psi. And I want you to determine the normal stress and the maximum shear stress in the spherical caps, so here, and then the stresses in directions perpendicular and parallel to the helical weld. So we're going to be looking at basically the stress element that's on its side. So this is the sample problem we're going to do right now. Let me switch over to the document camera. Hold on. All right. So here we are. Yeah, this is live. This is working. Okay. So part A is to look at the spherical caps, right? Let's just consider what's going on here. Let's see. We have a few things. This is not necessarily part of the problem, but I do want to bring this up. So consider you have a shell wall, right, of a certain thickness here. If you have 180 psig on the inside, right? This is gauge pressure. So we only have to worry about gauge pressure. And this is why a lot of cylindrical manufacturers pressure vessel, the the specs and stuff are listed in PSIG. You don't have to worry. You typically use these things at atmospheric pressure, right? So there's 14.7 psi on the outside. This is an absolute pressure, right? So internal, you actually have 194.7 psia, right? But because you have 14.7 on the outside, right? Those two, basically the 14.7 on the outside and the 14.7 on the inside cancel out. So you wind up with a net 180 psig on the inside. So you guys should remember this from thermo. Yeah, so that's one of the things that tie these things together. Also, remember for thin-walled analysis, R over T should be greater than or equal to 10. So what is that? R is, where is R? Oh, 30 inches OD, so R is 30 inches, and thickness is, we'll take the bigger one, 3/8. And this is going to be, basically, well, did I take, not 30, it should be 15. Radius is 15. I was like, that doesn't look right. Yeah, so 15 divided by 3 is 5 times 8 is 40, right? So that's okay. That means you can use the thin wall pressure analysis assumptions. Okay, so let's look at a component of this. A stress element anywhere on the sphere. Let's just draw it like this. We've got sigma 1 and sigma 2, and the analysis assumes that this is sigma equals 0, the sigma, or you can call it sigma 3. So this is normal. So this would be, inside pressure. This is an element, on the outside here, right? Sigma 1 and sigma 2. Now for a sphere, right, for spherical caps, sigma 1 equals sigma 2, and that's equal to PR over 2T. This is equation 7.36 in your text. Our actual radius is technically, it's not 15. The radius is actually 15 inches minus the wall thickness. So for the sphere, we've got, not 15, 5/16 inch. So the radius is 15 minus 5/16 inch. And this is going to equal 14.6875 inches. So sigma 1 equals, we've got 180 psi, and we've got a radius of 14.6875 inches. 2, and then the thickness here is 5/16 of an inch. So we wind up with a sigma of 4230 psi. And remember, that's in both directions for a sphere. This is just sigma 1 and sigma 2. So this is the normal stresses, right? These are the normal stresses in the sphere. Normal stresses. All right. For a spherical shell, we know just from the, in the text, I'm trying to remember if this was in the video, tau max is just equal to 1/2 sigma. This is actually explained in your text using a Mohr's circle, but it's basically because both your sigmas are the same, right? Sigma 1 and sigma 2 are the same. Your Mohr's circle looks kind of like this. You've got this point here. This is sigma 1 and sigma 2, right? And you wind up with a circle that goes around like that to 0. Because there is an orientation where you have, so you have an orientation where you have a tau max, right? It's just the radius of the circle, which is just 1/2 sigma 1. So tau max equals 1/2 4230, which equals, and I write this down, so tau max, 2115 psi. This, I should mention, this 0 actually comes from the 3D analysis, right? So if you want, hopefully you watch the video on the 3D analysis, which shows you can make the overall circle. Ideally, this is happening, well, not ideally, but this is basically happening in the plane tangent to the surface of the vessel. So that's where you're finding that that shear stress. Let's see, max shear stress is 0. Yeah, all right. So that's part A. Let me just label this part A. Part B is looking at the stresses in directions perpendicular and parallel to the helical weld. All right, so let's just pretend for a minute here you're some kind of element on this cylinder, right? So if you're a little element on this cylinder, any point in that cylinder you're going to have, and remember they define sigma 1 and sigma 2. Sigma 1 is the hoop stress, right? This is the stress. If you were to cut this cylinder this way, right, and look at a hoop, that's the stress around the hoop, right? And sigma 2 is the longitudinal stress. And that's the stress along the length of the cylinder. And remember, that's typically the lower value. Well, it is the lower value. So sigma 1 is, so what we have to do first is we have to find, for a given element, we have to find these stresses, right? The hoop stress and the longitudinal stress. Then we can look at the orientation of the weld, and we can use Mohr's circle to reorient this element to align with the weld and figure out the normal stresses and shear stresses on the weld, right? So the stress perpendicular to the weld is going to be the normal stress at that angle, and parallel to the weld is going to be the shear stress. So let's look at this. So first let's figure this out. Sigma 2, sigma 1. I mean, they're equal and opposite, right? So sigma 1 is just PR over T. And what do we have here? We've got, this is 180 psi. And R here we have a different thickness. So that's going to be 15 minus 3/8 over, 3/8. Let me just write the numbers in here. 180 times 14.625 over 3/8. This gives you 7020 psi. So that's sigma 1. Let me write this in up here on the diagram. Just remember they're using English units. I'm not going to crowd up that diagram too much. Sigma 2 is the longitudinal stress, and that's given by the equation PR over 2T, right? It's half of the hoop stress, so it's just 1/2 sigma 1, and that's going to be 70/20, so that's 3510 psi. So that's here. Oh, I said I wasn't going to write units, and then I did. I'm a liar. All right. So now let's see if I can fit this on here. We're going to use Moore's circle here. I'm going to pause this for a minute. Okay, this is not really the most legitimate way to draw Moore's circle. I do the circle first without actually drawing any of the, putting any of the information on there. And this is really not to scale, because if you know, you'll notice here, this is this point here is the 70/20, right? This is sigma 1. In your textbook, they use axes A and B. So instead of X and Y, because these are oriented along the cylinder, right? Anywhere along the cylinder wall. So they just use A as sort of the one that runs along the curve of the cylinder, and then B that runs along the longitudinal length. So we'll use those. We'll use that notation. Let's see. This is the A axis, and then here we've got 3510, and this is the B axis, and this is also sigma 2. Right? So here's your Moore's circle, and this one in the middle is just the difference, right? Let's just write this out. I'll call this point C, right? So sigma C is just, we've got sigma 1 plus sigma 2 over 2, which is just, what's the average of the two, right? So it's 5261 psi. Or sorry, 65. Geez. So this is 5265. 5265 right here. I mean, you could take the difference, divide the difference by 2, and then add it to the bottom, but that's just a nuisance. So it's just the average. The radius, right, R, is going to be sigma 2 minus, well, sigma 1, I guess. Sigma 1 minus sigma 2 over 2. Right, it's just the difference between these two divided by 2. And that's going to be, what do we get? 1755 psi. So that's the radius. Now we have theta of the weld, right? The theta of the weld is 25 degrees. I'm going to have to go to another sheet of paper here. Let's see, do I have one? Oops, this is another problem. I'm afraid to pause my video again. Sample problem 7.5 continued. All right, so we have this element that's angled, right? And this is angled at 25 degrees. So picture, let's see. I should put a little line here. This is the weld, right? The surface of the weld runs along this way. And this is, we're going to call this, so notice my axes, right? Sigma 2 is B axis. So I'm going to call this, oh geez, did I mislabel these? Hold on a second. B prime. Let's see what I do. Don't think I mislabeled these. TW 35. No, this is is not mislabeled. This is the A prime axis. Sorry. This is, oops. This one up here. Yeah, these are not mislabeled. Okay, so we're taking this and we're angling it, and this is B prime. Yeah, so I had a wrote my notes wrong. This is correct up here. Sigma 2 is along B. We've rotated this element, so this is B prime. Sorry about the confusion, guys. All right, so we're looking for the normal stress, right, along this weld. So this is going to be sigma B prime. So now if we look at Moore's circle here, remember theta is 25. So in Moore's world, 2 theta is 50 degrees, right? So we're going to rotate this whole thing, this whole axis by 50 degrees. And I'm not going to claim to draw the correct angle, but I'm going to try to draw something more than 45 degrees. I'll use red. All right, so here I have 50 degrees. And notice here I also have 50 degrees. Right? So this is where it's getting a little confusing, is because you started off with Moore's circle using X and Y, but we're switching over to A and B. So A is the maximum, B is the minimum. So notice now I've rotated both of these axes. This is A prime and this is B prime here. So what you can do is you can basically use this triangle here. Let's see, how am I going to draw this? B prime. This is the radius, equal to 1755 psi. Right, this is the angle of 50 degrees. So this is your this distance here, right, is over here. So we can find sigma B prime as equal to, so this would be sigma B prime, right? This is sigma B prime. Notice it's on the stress axis. This is going to be 52/65 minus cosine of 50, right? This is sigma B, well, that's just the length of it. Sigma B prime is actually right here. And this is 56 or 52/65, right? That's the length here, this length L. So this is cosine 50, right? Oops, I need the radius, R cosine 50. R cosine 50. Oh my God. All right. Yeah, I think I've tried to use too many diagrams to demonstrate a very simple concept. All we want is, we want to know the stress corresponding to the B prime point, and that's this. So here we have 52/65 minus R is 1755 times cosine 50, and we get sigma B prime equals 4137 psi. So that's what sigma B prime is, and that's up here. 4137 psi. So that is the normal stress on the weld, right? So this is the orientation of the weld. It is oriented 25 degrees, right? So look at the, from the vertical, right? This is also 25 degrees. Now we need to know the shear stress. So the shear stress is just, if we look at Moore's circle, right? The shear stress is just this value here. This is tau B prime. And that's the height of this triangle. So over here, that's this, tau B prime. So tau B prime is just equal to, we'll put a little, whoop, my screen froze, I don't know why. Okay, I think, oh, I gotta check my sound. You never have, okay, well I always have too many problems with this. All right, tau B prime is just gonna be R sine of 50. So this is just 1755 sine of 50 degrees, and tau B prime equals 1344 psi. Now notice where it is on the Moore's circle. So I drew this, remember, the bottom, well, you can use clockwise. The clock is above the counter, right? So counterclockwise is below, clockwise is above. Or you can just remember down here is the positive, right? And up here is the negative. It's just flipped. Any way you remember it, this indicates a clockwise rotation on the element, right? So that means the shear is going to be acting in this direction. So here we have tau of the weld equals 1344 psi. So the actual answers to this is stress perpendicular to weld equals, it's the sigma B prime, right, 4137 psi. And the stress, the shear stress, let's see, this is stress parallel to the, well, by definition, shear stress is parallel. So the shear stress of the weld is going to be, what did I say, 1344 psi. So those are your answers for part B. And this is what it looks like on the element, right? So this is the usefulness of being able to calculate stresses and then rotate them to different angles, right? You may have you may have a weld that, and this happens a lot, right? You have a vessel, and maybe the vessel itself is made up of just rectangular plates, and things are welded along the longitudinal. Maybe things are welded sort of this way and that way, but you may actually have to do something, at a port or some kind of manway or something where things are, welds are not necessarily in the same directions as you want, right? Especially if it's a circular weld, you're going to have to look at, all right, all the different angles. But you may have to weld at some angle, and knowing that stress or knowing how to calculate that stress is important for structural analysis. So yeah, this is the sample problem 7.5. Thanks for watching. Oh, where's my mouse?